Hi, and welcome to Lab 3, the black hole. These labs are getting so much more interesting. We're going to start with the introduction. So in this lab, we have a star that is orbiting a black hole of an unknown mass that is located at the origin. We have a few givens, the mass of the star, and we're supposed to analyze the star's motion over 1 day from all points in the data set. And the force that is acting on the star would be our black hole. So some of the things that we are trying to describe is the relationship between the net force and the parallel and the perpendicular direction, and also the change in momentum in the parallel and perpendicular direction. Sorry, I don't know why that was such a slip up. And how the position data can tell us more about, like forces acting on the object, which the only force that should be acting on the object right now, our star, is the black hole. And then deriving the mass of that black hole based on the points in our data set. So here we have our big idea. Yes. Some of the things we've been going over, of course, Newton's second law, the momentum principle, and now we're getting onto the gravitational constant and what that means. Here we have our kissing circle and some more images to further show you, what we are analyzing in our lab. So we have our two masses, or two objects that are acting on one another. And it's also showing its orbital motion. Just to reiterate Newton's second law, the rate of change of momentum of the object is directly proportional to the resultant force applied and is in the direction of the force. And then we have our momentum principle, which is, of course, the F net times the change in time. So next, here is my code. This was some of the preliminary stuff that we weren't supposed to edit, but of course I added my email in, which gave us a unique data set. Some of the givens were the gravitational constant, the star's mass, and the change. Of course, we have our change in time for 1 day. So we have our gravitational constant was 6.7 e to the negative 11. We have our star's mass, which is 2.08 times 10 raised to the 30th power. Delta T is 400 for the seconds in total for 1 day. On our next slide, we have a few more images describing the kissing circle and the parallel and perpendicular motion. So in our code, we take our initial and final velocity first, and then we also take our initial and final momentum. Or rather, we find the initial and final momentum vectors. Delta V equals V final minus V initial, delta P the same. We have dp dt, which is delta P over delta T, or F net, which would be dp dt. We have our P hat, our momentum, which is P initial over the magnitude of P initial. We have our dmag P dt, which is our magnitude of the P final minus P initial over delta T. Our dp dt dp dt and the parallel position equals P hat over dmag P dt. We have our F net in the parallel position equals dBdt equals also in the parallel position. Then we go into our perpendicular, which would be the dPdt minus the parallel. Finally, we get down to calculating our mass of the black hole, which we have our distance would be the origin minus the star's position. The mass of the black hole would equal the magnitude of F net times the magnitude of R raised to the 2 over G gravitational constant times the star's mass, which takes us on to our last slide. One correction I'd like to make, my arrow scale is actually 1 times 10 to the negative 17. But I didn't get to go back and change it because the scale of the arrow is actually very small. So I set up my arrows. We have our pink arrow, which is going in the direction of the star. We have another arrow, which is going in the parallel motion, and another arrow, which is going in our perpendicular motion. And we do this for a total of 1 day. And then my final values with FNet would be 8.9 raised to the 28th power. My FNet in the parallel direction would be 3.01. raised to the 28th power, and my F net perpendicular would be 8.3 raised to the 28th power. All very, very, very large values. So just some really, really quick final remarks on the questions at the end of our lab. The biggest thing about the what does it mean question is that the momentum describes the object's motion, while the force, on the other hand, in the perpendicular and parallel positions or directions, is that describes what causes the object to move.